Welcome back to Deep Learning. So today we want to look at a couple of initialization techniques that will come in really handy throughout your work with deep learning networks.
And there is very little theory behind the best solutions that we have at the moment.
So you may wonder, why does initialization matter? If you have a convex function, actually it doesn't matter at all, because you follow the negative gradient direction and you will always find the global minimum. So no problem for convex optimization. However, many of the problems that we are dealing with are non-convex, and a non-convex function may have different local minima. And now if I start at this point, you can see that I achieve one local minimum by the optimization. But if I were to start at this point, you can see that I would end up with a very different local minimum. So for non-convex problems, initialization is actually a big deal, and neural networks with nonlinearity are in general non-convex. So what can be done? Well, of course you have to work with some initialization, and for the biases you can work quite easily and initialize them to 0. So this is very typical. Keep in mind that if you're working with ReLUs, you may want to start with a small positive constant, because this is better because of the dying ReLU issue.
We are happy that it works better than any competing method.
For the weights, well, for the weights you need to be random to break the symmetry. We already had this problem in Dropout, that we need additional regularization in order to break the symmetry. And it would be especially bad to initialize them with zeros, because then the gradient is 0. So this is something that you don't want to do.
Because it doesn't work.
Similar to the learning rate, their variance influences the stability of the learning process. So small, uniform, Gaussian values work. Now you may wonder, how can we calibrate those variances? And let's suppose we have a single linear neuron with weights W and input X. And remember that the capital letters here mark them as random variables. Then you can see that the output is W times X. So this is this linear combination of the respective inputs plus some bias. And now we are interested in the variance of Y hat. If we assume that W and X are independent, then the variance of every product can be actually computed as the expected value of X to the power of 2 times the variance of W, plus the expected value of W to the power of 2 times the variance of X, and then you add the variances of the two random variables. Now, if we have W and X to have 0 mean, then this would simplify the whole issue, because the means would be 0, so the expected values cancel out, and our variance would simply the multiplication of the two variants. Now we assume that Xn and Wn are independent and identically distributed. In this special case, we can then see that essentially the n here scales our variances. So it's actually dependent on the number of inputs that you have towards your layer, and this is a scale of the variance with your Wn. So you see that the weights are very important, and effectively the more weights you have, the more it scales the variance.
Machine learning is the science of sloppiness, really.
As a result, we then can work with Xavier initialization. So we calibrate the variances for the forward pass. We initialize with a zero mean Gaussian, and we simply set the standard deviation to 1 over fan in, where fan in is the input dimension of the weights. So we simply scale the variance to be 1 over the number of input dimensions. In the backward pass, however, we would need the same effect backwards, so we would have to scale the standard deviation with 1 over fan out, where fan out is the output dimension of the weights. So you just average those two and compute a new standard deviation, and this initialization is called after the first author of reference 21. Well, what else can be done? There's he initialization, which then also considers that the assumption of linear neurons is a problem. So in reference 12, they showed that for ReLUs, it's better to actually use the square root of 2 over fan-in as standard deviation. So this is a very typical choice for initializing the weights randomly. Then other conventional initial choices is that you do L2 regularization. You use dropout with a probability of 0.5 for fully connected layers, and you use them selectively in convolutional neural networks. You do mean subtraction, batch normalization, and he initialization. So this is the very typical setup. Okay, so what other tricks of the trade do we have left? One important technique is transfer learning.
So that is transfer learning, and it has been done in principle for many decades.
Now, transfer learning is typically used in all situations where you have few data. One example are medical data sets. There you typically have very few data available. So the idea is then to reuse models trained on ImageNet, for example. So you can even reuse things that have been trained on a different task for the same data. You can also use different data for the same task, or you can even do different data on a different task. So now the question is, what should we transfer? Well, the convolutional layers extract features, and the expectation now is that less task-specific features are in earlier layers. We have seen that in a couple of papers. We can also see that in our videos on visualization. So typically those have more basic information and are likely to contain information that is worth transferring.
The stuff that works best is really simple.
So we cut the network at some depth in the feature extraction part. And for those extracted parts, we can, for example, fix the learning rate to 0. So if we set eta to 0, they won't change. Or you can start fine-tuning them. One example here is skin cancer classification. Here they use a deep convolutional neural network based on Inception v3. And they have essentially a state-of-the-art architecture that was pre-trained on ImageNet. And then they fine-tune it on skin cancer data. So they essentially take the network, they change the weights slightly, and what you have to replace is essentially the right-hand part, the training of the classes. This is something that you won't find in ImageNet, so there you have to replace the entire network because you want to predict very different classes. But then you can use a couple of fully connected layers in order to make your feature representations learned and mapped to a different space, and then you can do the classification from there.
Of the world in vector space. But I think this is very difficult for normal people to understand. They would not know what the heck they're looking at.
So there's also transfer between modalities. This was also found to be beneficial. Now you can transfer from color to X-ray, and here it's actually sufficient to simply copy the input 3 times. And then you don't need that much fine-tuning. So this works pretty well. One alternative is that you use feature representations of other networks as a loss function. This then leads to perceptual loss. We will talk about perceptual loss in a different video. In any case, transfer learning is typically a very good idea, and there's many applications, many papers where they have been using transfer learning. A longer time ago, they didn't say transfer learning, but they said adaptation. So also in speech processing, they have speaker adaptation and noise adaptation and so on. But nowadays you say transfer learning, but it's essentially the same concept. Okay, so next time in deep learning, we will talk about the remaining tricks of the trade and regularization. And I'm looking forward to present you this in the next video. So thank you very much for listening. Goodbye.